welcome to SciLux, the podcast where we talk about scientific developments and technological changes, sometimes in Luxembourg, sometimes not, but this time again in Luxembourg, which means we are proudly supported by Research Luxembourg and recording at the Media Center of the University of Luxembourg. And today it's also a special episode because we are talking because of the Quantum Year and Quantum Day, so there'll be a lot of quantum mentioned. And this means that we have two special guests from SNT. We have Professor Peter Roenne, who trained as a theoretical physicist, and he holds a PhD in mathematical physics from the University of London. Currently, Peter leads the Applied Security and Information Assurance Group, APSIA, at SNT. And then we have Dr. Peter Roenne, who received his PhD in theoretical physics from the University of Copenhagen. Currently, he works in the APSIA group headed by Professor Roenne. Peter and Peter, thank you very much for coming today.
Hello.
It's very good that you have the same name because I have these personal statistics on the names of people appearing in my podcast, and I had the feeling that at a certain moment everybody was called Alex. So I had Alexandros, I had Alex, and I was like, what is it? Do you have to be called Alex to be a researcher? So now we have two Peters, which is good. We are proving that this is really a question of sampling rather than anything else, right? Okay, I said we were talking about quantum, so let's start with a very general question, right? This quantum year, quantum mechanics, quantum day, everything quantum. So we should be talking more about it. So what is quantum, I'm going to say quantum mechanics for you, and what are you looking forward to in the field, Peter?
So that's quite a big question.
Yes, I know. We could talk for the next 50 minutes about it, I'm sure.
It is a big topic. So in the last millennium, if you like, there were two major revolutions in theoretical physics, which is to say, the way we try to understand the universe around us. So one was relativity, special and general and so on. So that's changed completely the way we think about space and time, space-time. And the other, of course, was quantum mechanics. Both of them sort of came fairly early on in the previous century. And so, quantum mechanics is all about trying to understand things at the subatomic level. And basically it turns out that the laws at that level are completely different from what we're familiar with at the more macroscopic level, the classical physics of Newton and so on. So it's meant a complete change in the way we think about the nature of reality, the nature of matter, the nature of forces and things. So conceptually it's very important, but also at a practical level, of course, it's led to many, many innovations, which I guess we'll get onto more about that later on. I mean, part of it is that it's pretty weird. It's very counterintuitive. Feynman, I think, said something like, if you think you understand quantum mechanics, you don't. Nobody really fully understands. But that just seems to be the way nature is. So we have to sort of live with it and try and get our heads around it.
Anything to add to this? I think it was a pretty good summary, right?
Yes, it was a very good summary. I come from a background in string theory, and for me, quantum physics was always about understanding the nature itself, understanding what is the underlying principles we have here. And quantum mechanics, quantum physics is just very interesting and intriguing. You'll see so many different relations. And now with going into quantum information theory, you have these special no-go theorems that tells you what you can do, what you can't do, which is also like mind-baffling sometimes. So yeah, right now, today we are like surrounded by technique that is building on quantum physics. Everything we look around, it's basically building on our knowledge about quantum physics. Even also where we don't see it, like GPS has an atomic clock behind it. So yeah, we're living in very interesting times because now we will have this new quantum revolution perhaps coming around with quantum computers and seeing what they can do.
Yeah, I like the fact that you added the word perhaps, right? Because we're all in starting blocks a little bit. I don't know if you noticed, I think it was 1 or 2 days ago, there was a discussion of a new quantum algorithm. It's always like, is this that one that will be then maybe find more applications for quantum computers or not really? And there's always something, right? Also because the industry is on board. So there is always the discussion of, what Google has done, what's been done in China. So it kind of is fueled as well, I guess, right?
Is this the D-Wave thing?
Yeah, I think so, yes. I was reading something on Quantum magazine. I don't know, I don't remember the name, but it was, yes, I'm going to share.
Well, there's certainly a bragging race going on, right? You see like gigantic numbers just being thrown out and And that's our job, to try to understand what is really up and down and what are the real limits. And then,
Yeah, and if you want to know more, listeners, about quantum computers themselves, 1 week ago there was a podcast with Professor Ignacio Sirac. We were talking about only quantum computers, because today we'll have cryptography, right? So for me, what is fascinating about your work is that basically you're preparing for something that does not exist yet. Am I right? Because we don't really have quantum computers.
Well, we have small-scale experimental computers, but we certainly don't have large-scale quantum computers that could tackle serious and cryptographic scale problems.
So how can you prepare for that if it's not full-scale?
Well, I mean, in theory, we know what a quantum computer is capable of. Well, actually, even there's questions, but we know some things that it can do, and in particular, things that it can do exponentially faster than a classical computer. And so we know that if someone does manage to build a large-scale quantum computer, we actually know algorithms which can break a lot of current cryptography. So in that sense, we understand what the threat is. It is still a hypothetical threat. I mean, it is conceivable that large-scale computers will be decades away, or maybe never even achievable. And there are people out there who argue that it's technically impossible to build. And there's a debate in the community about this. But I think most people think realistically that it will come about. I mean, it's basically engineering problems, some theory too, but it'll happen. So it's a threat which people need to take seriously. And I mean, that's witnessed by the fact that, for example, NIST, the National Institute for Standards and Technology in the US, has been running these competitions to develop algorithms which we hope will be resistant to the quantum threat, as it's called.
Yeah, I get that. One of the things I noticed when I was reading about your research is that sometimes you talk about quantum cryptography and sometimes post-quantum cryptography. Any one of you can tell me what is the difference?
So post-quantum cryptography is basically about using classical computers to do cryptography, to try to secure communication using certain different assumptions that you assume that some certain problem cannot be solved by a quantum computer. So currently we have like classical cryptography, which relies on, it's very hard for normal computers to actually factorize large numbers. So this is the RSA algorithm that's being used to communicate via the internet currently. But it was shown by Peter Shor that there is an algorithm for quantum computers that can actually factorize large numbers much more efficiently than you can do on classical computers, or what we know we can do on classical computers, certainly. So that means that you need to drop that assumption and say we cannot use this classical cryptography, we need to move to something else. And then the question is, what do you put instead? And now people have come up with different assumptions that we believe cannot be broken by quantum computers. Some of them have been shown to be broken even by classical computers. That's how it goes in research. But some of them have not been broken yet. And we build in cryptography now for computers today that we hope cannot be broken tomorrow by quantum computers.
But not necessarily using quantum computers to do that.
Not just plain classical computers.
And this is your specialization.
This is one of our specializations. We look both into post-quantum cryptography, classical cryptography, because that's still important, because it will take probably a long time to build these computers, and then also quantum cryptography.
You said factorize large numbers. I'm not sure everyone will know what this is, and it's not so complicated. So let's explain, what does it mean, factorize large numbers? What does cryptography do?
Well, so a lot of cryptography depends on the notion of what are called one-way functions. So functions which are easy to compute in one direction, but extremely difficult, intractable in some sense, to compute in the other direction. So, multiplying two numbers together is pretty straightforward. I mean, we all learn that in school. And I mean, if they're big numbers, it gets laborious, but it's still, you can do it even on pen and paper in principle in finite time. But if you're given the product, say, of two very large primes with hundreds of digits each, and you're asked to, say, work out what are the two numbers multiplied together, give you that number, then that is extremely difficult to do it in that direction. Factorization, so multiplication is easy that direction. Factorizing is, as far as we know, essentially intractable, at least in classical terms.
So basically reversing that.
To reverse the process, yes. So you're given the product and you're asked to find the numbers which multiply together, give that product. And that's precisely where Shor's algorithm kicks in, because you actually get an exponential speed up. Go slightly technical for a moment. If you can attack it with Shor's algorithm with a quantum computer, And so the task becomes comparatively easy, kind of almost as easy, I guess, as multiplication for that matter, really. They become, I guess, almost equivalent in terms of complexity. Does that clarify a little bit?
Absolutely, yes. Yes, at least for me, hopefully for the listeners as well. But what is confusing to me, and I never had a chance to read on cryptography this much, is that sometimes it's just large numbers and sometimes it's prime numbers. Are these two different algorithms that we're talking about, or not really?
Well, with the RSA algorithm, which uses this notion of, it's large prime numbers.
Okay.
So it's the combination, right?
Well, why prime numbers?
If you were just to start with a randomly chosen number, it would probably have lots of small prime factors. There's a 50% chance it's going to be an even number, for example. So immediately you find a factor too. Finding small factors is pretty easy. You just start experimentally dividing through by the small numbers. And of course, each time the number will get smaller and smaller, so the task gets easier. So the point about taking the product of two large primes is that that's not going to happen. You either hit one of the primes and then you've solved it, or you don't.
Okay. Yes, I got it.
That's kind of why it becomes a sort of brute force. You basically more or less have to search all numbers, from one, up to the square root of the number you're given.
But you're absolutely on the right track, because there has been crypto systems that have been broken by having such smaller prime numbers in there, and they just overlook them. So if you use those, actually the security would be broken, and you can decrypt the messages you shouldn't be able to decrypt.
Thank you for that, because I had a feeling that I'm asking a stupid question at certain moments. No. Okay, good. So that's the traditional cryptography. So what's going on with the other two cryptographies then? How do you want to code it? How can you explain this at all?
Yeah, so they have some very different special assumptions, which might look harder, more advanced mathematics behind it. So some are built on isogenies of elliptic curves. So that sounds very advanced, and it is quite advanced mathematical objects. There are not too many experts in this field right now. So that's also why some of them actually was broken quite fast, because not too many people have worked on this and looked at this. We also have some which have been looked at for a longer time, which is based on error-correcting codes. We have some which are based on lattice-based assumptions. And then we have something for like signing, where it's actually based on hash functions. So these are these uninvertible functions. These are the main families that we are looking at right now. But yeah, it's still an ongoing research to actually try to prove as well as you can that these are secure. You cannot prove completely, but you can try to test it. And this is where you certainly have to know a lot about quantum computers theoretically, right? Because to be able to assess how secure is this, you need to figure out what is the best algorithm you can run on this quantum computer, which we, by the way, don't have. You cannot, test. You need to logically think, what can we do here? How much RAM would such a quantum computer be able to have in quantum memory? And how fast can it run? How many gates? So, for example, for Shor's algorithms, you would need something like 4,000 logical qubits, but then also millions of gates in quantum computers, as you maybe heard in the last podcast, is something like additions and multiplications in normal classical computers.
So as you need to know a little bit theoretically quantum computers, I think there is one thing we can define, so we don't get into the whole discussion, but one thing that you already mentioned, and maybe not everybody knows still, or did not listen to the previous episode, please do, at certain one, not good exactly, are the qubits. I think we have to say that because we will be discussing them for sure. What are qubits?
In essence, they're the quantum analog of classical bits, but classical bits just have two states, 0, 1, so they're kind of quite simple. Qubits, as is the nature of quantum mechanics, are much more subtle things. They basically have an infinite number of possibilities, so they're much, much richer. That said, of course, if you want to try and access a qubit, then you basically have to perform a measurement, and what happens then is the state collapses. Technically, you'll get a 0 or 1, usually with some probability. And the probability depends on the state and on the choice of measurement you make. So there's much richer information in a qubit, but on the other hand, we have very limited sort of access to that rich information, which is why the design of quantum algorithms is very, very subtle. Because you have all this extra richness of information bubbling under the surface, but your access to it is very restricted, and ultimately you have to get an output, so you have to make some sort of measurement at the ends. So you have to design things very carefully so that you make the right measurement at the ends and you make the right interactions between the qubits, so that you'll lead to your result. So you need a very different way of thinking about quantum algorithms as opposed to classical algorithms. Do you want to add something, Peter?
So this qubit, it can be 0 or 1, but what you have in quantum mechanics is you also have this superposition. So it can be 0 and 1 at the same time. And you probably know this from the Schrödinger cat in a box that is like dead or alive, but it's not an or. It's actually dead and alive at the same time until you try to look at it. And that means that if you have one of those qubits, you have something, but you don't know what it is. It could be a superposition, and this superposition is actually like a linear combination. So there's a lot of different possibilities between the 0 and the 1. And that's what you can use in quantum computers to make computation much, much faster. But it's also something that we use in the quantum cryptography to ensure security and secure communications if you are able to communicate with quantum medium.
You said it's very counterintuitive. So, of course, my intuition is not coping very well with this whole idea. And one of the things I don't understand is how can you actually have this threat of someone getting the information, stealing, hacking, however you want to call it, if clearly we know that the moment you observe the qubits you're using, I mean, you know it's a 0 or a 1, so people will know that they were disturbed. They will be observed. They will be measured. So why is this a problem? We should already know someone is trying to get into the system, right?
I mean, that's a good observation, and that's actually key to the way quantum cryptography works as opposed to post-quantum cryptography. Perhaps just to jump back a bit. So as Peter was saying, post-quantum crypto is basically classical, but designed with quantum computers and the quantum threat in mind. Whereas quantum crypto actually does use quantum phenomena. And so one of the things we've worked a lot on is quantum key. Well, I call it establishment. People commonly call it distribution, which I think is bad terminology. But anyway, allow me to call it establishment. And so this allows two people to establish a secret shared classical key, but by exchanging quantum states. And I guess we won't have the time or a visual whiteboard to go through all the details. But in essence, what's going on, it's related to what you were just saying. I mean, it exploits things like the Heisenberg uncertainty principle and things like the no cloning theorem, that you can't make a copy. If you're given an arbitrary quantum state, it's impossible to make an exact copy of the state without destroying the original. So in essence, what happens is they exchange quantum states over a quantum channel. So, well, in the most common form, Alice, say, prepares quantum states, sends them to Bob over optical fiber or through the vacuum of space or whatever. And Bob makes various measurements on them according to certain sort of protocols and rules. And then after that, then they switch into classical communication and they make sort of various comparisons. And the whole point of that is that if someone tries to eavesdrop on the quantum channel, i.e. measure the quantum states as they're going past, because of Heisenberg uncertainty, they will necessarily perturb those states. And that will produce measurable, detectable mismatches when the two parties, Alice and Bob, do the comparison at the end. So in that sense, we are exploiting the property, as you were sort of indicating. We're using it to positive effect. So maybe that also helps sort of draw the distinction between post-quantum crypto and proper quantum crypto.
Yes, it does for sure. I was just wondering because, of course, we're not talking about millions of qubits right now in the quantum computer. Hopefully one day, but pretty limited. Growing, but pretty limited. So if you were to actually do quantum cryptography on a quantum computer, what is the percentage of qubits that you would actually need to do the cryptography on it?
Well, to do quantum crypto, a particular quantum key exchange, you don't actually need a quantum computer. Basically, you just need, Alice needs something that can produce ideally single pulse photons with certain polarizations and sends them to Bob, who measures them with a polarizing filter or something. So you don't need a quantum computer. You need very sort of fairly elementary, simple apparatus. And the process basically happens on a sort of individual quantum state basis. Alice sends a photon and Bob measures it and so on. So you don't face all the complexities that you have with a quantum computer, where you're having to deal with potentially millions of quantum states, which need to be carefully entangled and so on and so forth. So it's much more manageable from an engineering point of view. And indeed, there are commercial kit to do quantum key establishment available. And we have projects which are testing out networks using this kit, including via satellites and so on and so forth. You're not in the scale of problem, and the scaling problems are not the same as they are for a quantum computer.
So what are the challenges then?
No, but I think you touch on a very important and interesting aspect, is that right now we're on the border of having the quantum computers, and what we also are on the border of having is short-lived quantum memory. And with this, you can really push this from just going from this quantum key exchange. You can get to some new kinds of quantum communication that we have been looking into and published on. And as soon as you get a little bit of quantum memory, you can do like quite cool stuff. You can have something like you can put some data in a quantum cloud, and I can actually ask for a secure deletion of my data, which you cannot ever achieve classically, because classically we could always copy. But as Peter said, quantumly we cannot just copy data. We have this no cloning theorem that says that it's just impossible to clone the data. So using the new technologies, we are able to just go from the standard quantum key establishment to much nicer properties. Mm-hmm. Some of the things we have looked into is something like deniable communication, to have higher order privacy.
Okay, you avoided my question because you just commented on what Peter said. What are the challenges then? Oh.
The challenges to what? Sorry.
Let's start with quantum cryptography, then we talk post-quantum.
Quantum key establishment, if you like, is a kind of first step. It's the basic thing. As I said, there is equipment out there now. People are experimenting with it. I mean, there are still challenges there. In theory, such protocols should be able to give you so-called unconditional secrecy. So even an adversary with a quantum computer, or even an infinitely powerful computer, shouldn't be able to break the secrecy of your channel, basically because of the point that you can always detect an eavesdropper. So that's an interesting thing, and that's the big sort of selling point for it. But I mean, there's still lots of challenges, engineering challenges. The people have found in practice attacks on such systems, even though in theory they should give perfect secrecy and so on. So there are still challenges, I guess, for QKE and so forth. But then, as Peter's indicating, there's a lot beyond that, because QKE, after all, just allows you to set up a secret classical key between Alice and Bob, and then they resort to conventional classical crypto block ciphers or something, or one-time pad. But we can go a lot beyond that. And, for example, we can think of ways that you can actually send your messages, your ciphertext, if you like, as quantum states. And then maybe you get things like deniability and so on, as Peter was saying. So there's a lot more beyond that, which I think has not really been very well explored. And I think there's a lot of potential that people haven't even yet conceived of, I think. That's the horizon. And I think there's still a lot out there which remains to be explored, even dreamt up.
Really about pushing the boundaries for what you can do when you have access to quantum communication. And you can now also combine it with this post-quantum cryptography. So we talked about this post-quantum cryptography, which you have on classical computers. But if you really assume that it's hard for quantum computers to break this, then you could think about attackers that are not like fully blown, computationally unbounded attackers that you have in the QKD case. But you can say like they're constrained to just having a quantum computer. And now you can combine this quantum communication with the post-quantum, and you can achieve some properties that you would not have been able to achieve otherwise. For example, there has been a result that has shown that if you get a computation out of a quantum computer and you want to verify that it's correct, then you can do it using some of these quantum-safe methods.
Oh, I was looking at the clock and I realized normally it's in the very beginning of the podcast, but we've been chatting. There has been so much we forgot about the pub quiz question. So sorry, listeners, if you're waiting only for that. But I also wanted to define the qubit in order to actually ask the question. So Peter, if you can ask the question, and remember, listeners, only at the end of the podcast we are going to solve it.
Yeah, so the pub quiz question is, can you delete a qubit?
Very easy question, or not. Short, at least. No, easy is not a good one. It's a very short question. And remember the answer only at the end. Okay, so I think I'm kind of now at least clear on the quantum cryptography, post-quantum cryptography, but I was wondering, for post-quantum cryptography, do you need to use a supercomputer or not? Does this really require this amount of calculations, cryptography on a quantum computer?
To actually use the crypto, typically it does take more computational effort than conventional crypto, but not to the extent of needing a supercomputer. Yeah, I mean, these problems, I think you didn't mention, some of them are based on so-called lattices in high-dimensional spaces. And you typically need hundreds of dimensions and so on and so forth. So you are moving into areas where the computational effort is much heavier than it is with conventional crypto, but certainly not to the extent of needing supercomputers. So, I mean, we can implement these things on fairly conventional hardware.
It is actually research that is ongoing in the group. So we try to show that you can take this new post-quantum cryptography and you can implement it even on small chips that you might have in current hardware. And this is important because classical cryptography now has to be phased out, and you have what is called the quantum transformation. So everybody needs to move by 2030, 2035 to the new cryptography. And you have a lot of devices that are small, that is not tuned for actually doing this. So this is where we are doing like an effort to try to figure out how can you best implement the post-quantum cryptography software into small constrained devices, which is a very interesting challenge.
Of course, and then comes also the standardization and kind of sharing the same methods, which is always a challenge, isn't it?
It's a huge challenge. So this is where NIST has been leading this, but now everybody has come on. Now China is, Russia, Europe is trying to do something. All the different agencies, BSI, ANSI, so on, they have different recommendations for what to do.
We talked about sending information, right? And this need to use better cryptography for sending the information. But it's not the only very important case where we should look into quantum cryptography, right? I know that you also look into e-voting as one of the places where we really need good cryptography.
Yes, well, my group has done a lot of work on trying to make elections secure and verifiable and stuff like that. And certainly there you need to think about the quantum threat. So we have been working on incorporating post-quantum crypto into some of these designs. What we don't really have, I mean, I think there's some papers out there proposing where you actually use quantum to run elections. I think they're all rather flawed and broken and so on. So that's another big challenge, would be to come up with a nice quantum voting system. I don't believe anybody's done that. We've given thought to it, but...
Yeah, but we have already designed post-quantum voting schemes, and this is very important because in electronic voting schemes, a very important property is verifiability. So if we go and do an election, we want each and every voter to be able to verify that it was correctly calculated, the result. And they need to do this on public data. And this means that we have public data containing the votes of all the voters. And now if you have this and it's done with classical encryption and along comes a quantum computer, you have lost the privacy of the election. And that could even scare people today from voting the way they would like to.
But I can't verify my vote right now if it was counted correctly. So why do we need verify? I mean, it's not working right now.
Well, in conventional old-fashioned voting, where you just drop a piece of paper in a box and it's hand-counted and so on, then for sure there is no verification, certainly at the individual voter level. Typically there'll be observers who will watch the moving of the ballot boxes and the counting and so on and so forth. But you have to place a lot of trust in those processes. And as you know, particularly I guess over the last few decades, democracy elections have often been called into question, notably in the US. So that has been focusing people's minds, how to restore trust in democracy and elections. And the kind of approach that crypto people, information security people have tended to take is to introduce some kind of verifiability so that you don't have to blindly trust either the software or the hardware or the officials and so on and so forth. A colleague of ours speaks of evidence-based elections. So as Peter was saying, you design the system in such a way that as it runs, it produces evidence, sort of mathematical, cryptographic evidence, if you like, that it's processed all the votes correctly. There are fancy things like zero-knowledge proofs and so on, which are classical cryptographic concept, a super cool concept as well, where you basically can prove that you either know something or something is true, but without revealing the value or whatever. So that has motivated this whole idea of trying to make elections, evidence-based, and in particular, perhaps verifiable.
But what I see as a risk is that if I can verify how I voted, maybe I can sell my vote.
Exactly so, and that's why you have to be very careful about how you design these things to try and avoid dangers of vote buying, selling, coercion, and so on and so forth. And that's what really makes this such a, and you were asked about challenge as well. This is a big challenge, and one that, well, I for one have been grappling with for a couple of decades.
Are you getting closer to a solution?
Well, we're getting better and better. But, combining all the properties of very strong privacy notions, which include resistance against vote buyers and coercers and so on and so forth, on the one hand, and all the sort of verifiability that we've been talking about here, which is more a question of transparency and accountability and so on. These two things are in tension. And to try and do all this in a way that the system will actually be usable by the average person, the average voter, once every 4 years or something like that, to get all of that right is fiendishly difficult. And if you want to try and do it over the internet, it's even harder. So this has been keeping us busy for years.
It's certainly, we have been working on this for a long time, and this is really the challenge. You have to have a holistic approach here, right? You have voters who cannot use computers, smartphones very well, but they need to be able to do this to verify their votes. You need to have a secure protocol that you can prove is secure. You need to have an implementation that is also correct and doing what it should be doing. And then you have all of the authorities, you need the laws, you need to consider everything to solve these problems.
So something more positive maybe, because that's really a challenge. I don't want to leave our listeners with this, oh my God, how do you solve this? Any other projects? I've noticed that some of your projects are really difficult. I don't know who comes up with the abbreviations or the short forms, but I don't even know how to pronounce them. So one of them is it Lux QCI? That's just like that? Or how do you call it?
Lux QCI, yes, that's true. That's because
the other one is what? IntUQKD?
We didn't come up with that.
Okay, it's always, the answer is always, I can never find the people who actually came up with the names, but there had to be someone, right? Not the person in the room.
That was
it's easier to
one
blame.
of the companies in the consortium
Okay,
came up
fair
with that
enough.
acronym.
Fair enough.
And we've had some good acronyms in the past. One was Petrus.
Oh, I like that one.
Pablo was another one, yes. So we've had some...
Equivox for one voting project, so yeah.
Yeah. Okay. Sorry. I'm not complaining about it, but I just wanted to know, is there anything going on in these projects or any other projects that we haven't really covered right now that you would like to mention, what you're working on?
Yeah, so Lux QCI. QCI means quantum communication infrastructure. So now we are building this quantum communication infrastructure for Luxembourg. So this is with SES, with the university, with different players. And there will actually be QKD. There's a QKD line, for example, from here in Bilbao to Kirchberg. And in the other project, which is called IntUQKD, is together with Stereo and with Post Luxembourg, we actually have a QKD line between Luxembourg and Belgium. And there's actually going to be launched a satellite this summer. So there will be satellite communication. There's a ground station here in Luxembourg. There will be one in Singapore. There will be one in the UK. And you will actually have QKD satellite ground-based communication.
That's great.
So the INT actually stands for international. And the goal there was to try and go actually beyond Europe. So far people have been at the Luxembourg level and then in Europe. That aims to go beyond. Singapore, UK is included, right? And several countries outside Europe.
But for satellite communication, isn't there a problem of the distance? Because, when we're talking about Belgium, that's 40 kilometers probably, what you were sending here. It's a bit more than this, right?
Well, yes, they're much faster distances, but of course you have the advantage that a lot of that is in vacuum. So you don't have to deal so much with atmosphere.
But you do have to be careful about the Luxembourg clouds.
Well, yes. Absolutely.
But of course, we always have sunny days here.
Yeah, well, that probably is the same in the UK, right? I guess you can relate because you mentioned UK as a partner, so...
Don't mention it, but it's in Gibraltar, so...
Yeah.
Okay, cool. Well, I did not expect we'll be discussing the Luxembourg clouds, but it's true. Today it's a nice day, so we should be positive today. The quantum
today it would all work. Yeah,
it would all work. Exactly. All right, good. I think this is the moment to kind of wrap up and go back to our pub quiz question that you had for our listeners. Our listeners, remember, it was about deleting a qubit. So is it possible or not?
Actually, you cannot delete a qubit as such. So if you have even like 2 qubits, you could try to measure in one state and try to undo the other. But if you could take like 2 qubits and delete one of them, you would sort of end up with just 1 qubit. And what you would do if you look at this in reverse order, you would actually be able to make a clone. So if I run time backwards, you're going against the no-clone theorem. And you can also prove that I was able to delete a qubit. I could actually have superluminal communication. So it's not possible.
So now I'm not getting something. You just mentioned about quantum clouds and actually proper deleting of information and all that. But the qubit you can't delete.
That sounds like a contradiction. And there's a lot of things that sounds like a contradiction here. But that is because I know something about what's going on in the cloud. I'm going to store some information and I'm going to help the cloud and make the cloud prove that it verifiably deleted what I wanted to delete.
And the word delete here is kind of subtle. So the question is not as easy as it sounds.
Yeah, probably a different definition of delete.
Because you could destroy a qubit, right? You can try to just measure it, you can do something, but actually there's a conservation of information, we believe. This is one of the big questions, which is actually going down to like looking at black holes, what is going to happen at the horizon of black holes. Do we have information conservation? But in principle, if you have information conservation, then you cannot delete a qubit. They will just dissipate on more small degrees of freedom.
And this maybe came up in your earlier podcast about quantum computing. Quantum algorithms are basically reversible, or quantum computations, in contrast to classical, which often you can, if you take an XOR, you can't then recover the two input bits, whereas in a quantum computation, you can always run them in reverse, which is related to this sort of conservation of information result.
And that is also another challenge. I mean, if you can reverse it, then it's easier to go back to whatever was sent, right? Or not?
Well, it depends. I mean, as soon as you do a measurement, you actually...
Okay, yes, we're going back, yes,
Yeah.
Of course. Hopefully that's... Anyway, what remains is just to thank you very much for today. I hope it was a really good food for thought for our listeners, that they had to really focus to understand everything. And listeners, if you're interested in more, there'll be more. There's a lot going on for Quantum Year, quantum computers, Quantum Day and everything else. And also check what Peter and Peter are doing at SNT, because it's very, very interesting. Thank you very much for today.
Thank you.
Thank you.
And this is it for today. Don't forget to subscribe, to follow us, to check what we're doing on all the social media. Of course, if you have guests to suggest, do that too. And don't forget as well that we are on Patreon. So if you want to support our expansion, go there and support us too. This was Silax, and my name is Hanna Siemaszko.